Hi, this is Ahmed from the University of Toronto. This video will be to talk about the final course project of ECE 1508, Network Softwarization Technologies and Enablers. The course project topic is Machine Learning in Traffic Classification of SDN-based networks. The problem definition is as follows. Essentially, in today's IP networks, traffic classification has become an important research area, especially with the advancements in machine learning capability and SDN technology. Traditional traffic classification techniques using payload inspection have become ineffective due to the encrypted and dynamic nature of traffic, so we will attempt to use supervised and unsupervised machine learning models to classify the traffic flows based on features such as number and size of packets. So the testbed of this traffic classification algorithm is VirtualBox. There's no real advantage to using VirtualBox except the fact that it's easy to use and the fact that it can be locally deployed. However, any cloud-based infrastructure can be used, including Savvy. So as you can see in this network, we have 5 nodes, which are represented as VMs, 3 hosts, 1 switch, 1 controller. The black line represents the internal network in VirtualBox, which we will call the underlay network. The blue dotted lines represent the VXLAN tunnels connecting the host to the switch, which create the overlay network. The blue IP are the overlay IP. Overlay networks are required in this virtual setup because it simulates a real network where the traffic is forced through the switch. The connection between the switch and controller is just using the underlay network though. And as you can see, the Ryu controller was used. The main advantage is that Ryu is written in Python, so it's easier to integrate with the machine learning application, as most of those libraries are also written in Python. So the process that was followed in this project is that first we build the topology of the network. We set up VirtualBox, the host, the switch, the controller with the appropriate configuration and tools. Next we simulate the traffic, and the tool used to do that is the distributed internet traffic generator, and we'll discuss that in more detail later. We need to modify the controller script slightly to get output in a desired format, then collect the training data while the traffic is running between the hosts. We take the training data and use it to train 2 machine learning models, which we will go through in a Jupyter notebook. And then finally, we use the output of those models in the final traffic classification application to classify flows real time. So these diagrams are just to show how well the machine learning models do and compare them. For this project, 4 types of traffic were considered: DNS, Telnet, ping, and voice. For supervised learning, logistic regression was used, and for unsupervised learning, k-means clustering algorithm was used. In logistic regression, we get a pretty high accuracy and the boundaries are well defined. In the clustering algorithm, it's not performing as nicely because our data isn't clustered circularly, so it's more linear in shape, and the clustering algorithm, for example, assumes that this linearly shaped blob of data is actually 2 clusters. So now for the demonstration of the code. First we'll just go over what we already discussed, that this topology was deployed in VirtualBox, and we can see the VMs running here. Also, as mentioned earlier, the traffic simulation tool is called the Distributed Internet Traffic Generator, and this is the website, and we can find more information including documentation and some commands to run. So the first step is to collect training data. So the first step of that is to start a simple traffic flow. So we can just do a simple ping between host 3 and host 1. So we have that running. And then the command to collect the traffic data is using the traffic classifier script written in Python 3. And then the commands to collect training data are train, and then you type in the type of traffic that you're training for. So just to see where we change the timeout value. So this timeout value here represents how long the script will run to collect the training data. So right now it's actually set for 15 seconds already, so that's fine. So if we run the command, it will pick up the traffic that's running between host 3 and host 1, run for 15 seconds, and generate a CSV file. So we just sped it up a bit, and it says it's finished collecting the data, and as you can see that we have a a CSV file for the ping data. And we also have telnet, voice, and DNS, which were collected through the DITG tool. So we take these CSV files and we upload them to Jupyter Notebook to train the models. So I've already saved the Jupyter Notebook as HTML, so it's easy to read. What we do first is that we upload the CSV files, or convert the CSV data into data frame objects, and then concatenate the data frame objects to a single object. We drop any not any value or empty values in case the script, the training script finished before it collected a full row of data. We also drop the forward packets, forward bytes, reverse packets, reverse bytes, because this information just increases linearly and it's not very relative for the models. So what we see is that our data frame consists of about 5,000 rows and 13 columns, and the 13 columns represent 12 features and 1 target. So here's just some more information about the type of data we have, and the features again are depicted here. So first we start off with a logistic regression model. So our features are the X variable and our target is the Y variable. We split the data frame into a training and testing set, create the model, fit the model. We test it for a single prediction, so some random value here. I just chose 2,590, and we see that our model predicted voice, and it was actually voice, so it's a good sign. We convert the predicted results into a data frame, and we see it has a great accuracy, 99.68%. And then we save the linear or logistic regression model using the pickle library in Python. Some ways to visualize the accuracy of the model are through a confusion matrix and a PCA analysis, so we'll get through that in a bit. For the confusion matrix, it's basically showing how accurately it predicted the label. So for the true label, so let's say we have ping data, the predicted labels 352 out of 353 times it predicted accurately. And the reason these values are smaller is because we're only doing the test set right now, because we split the data frame earlier. Principal component analysis essentially just reduces our 12 features into 2 principal components. So we need to scale it and then fit a PCA. So it's helpful to visualize the data in 2 dimensions, because 12 dimensions is too hard to visualize. And we can see how the traffic is spread out in 2 dimensions. We have our telnet traffic, voice traffic, DNS, and ping are kind of clustered together here. So what we saw is that 84% of our data can be explained through 2 principal components, the variance in the data. So perhaps the other 16% would explain the difference between the DNS and ping. Logistic regression creates decision boundaries, and they're very clearly visualized in this graph here. So we can see it's doing a great job of splitting the telnet and the voice, and then it splits the ping and the DNS further, but it's a little bit difficult to see as it's kind of clustered in that area. So that's for logistic regression. Now for k-means clustering, which is an unsupervised model. So basically, supervised model, we tell it what it has to look for, which is the type of traffic. For unsupervised model, we just feed in the data and we kind of let it determine what or how the data is clustered. So when we fit in our X data, we see that it spits out 4 possible clusters and 12 features, or 12 dimensions of those. To visualize that, we have some basic images here, and it's just trying to show which features are important in our labels. And here we just kind of assign the traffic labels to the output of the k-means clustering algorithm. So it outputs a value between 0 and 3, and we just convert that into a label, DNS, ping, telnet, or voice. We see that it has a very poor performance of 30.5% accuracy, so it's basically just kind of guessing. And we discussed this earlier in our principal component analysis when we compare the true labels and the cluster labels. Clearly it's not very good at detecting linearly shaped clusters. It splits up the clusters and assumes that this is its own cluster, and the left side is its own cluster. So that's an issue with the unsupervised k-means clustering. Some other models can be experimented with, and that can be left for a future improvement of the algorithm. So again, we can use a confusion matrix just to visualize how accurate. Obviously, there's almost like nothing in the diagonals, so it shows that it's performing very poorly. And we save the model using the pickle library so we can use it for real-time analysis. Now we will run the traffic classification code. So we again use the Python 3 script. And instead of train, we type in either unsupervised or supervised. Let's go with supervised because we saw it had a better accuracy. So we run that. We get a little warning that the pickle versions are different. So we already had a ping running between host 3 and host 1. So it's showing, it picked that up and showing the state that as active between those two. So it's accurately classifying that traffic. Now let's run another traffic. This time we'll use the tool. So the way we run the ITG tool, we start the receiver on host 1. And then we send telnet traffic from host 2 to host 1. And we just put in a for loop because the telnet traffic doesn't last very long. So we'll just go through that 200 times. And we see here that it accurately picks up the telnet traffic too. And sometimes it's inactive because the telnet traffic is has more variance than the ping traffic, which is more consistent. So now we see that we have two traffics, ping and telnet, running. And if we stop the ping, we should see that it changes the ping traffic to inactive between the source and MAC. So this is happening in the layer 2 domain. So we use the source and destination MAC addresses instead of IP to determine or to identify the nodes. So that's the traffic classification script in action. And some limitations of this application include that it will only identify a single flow from one host to the other host because it's only using the source and destination pairs for the keys. So if we started voice traffic from this MAC to this MAC, it will confuse the algorithm and it'll assume it was just the previous ping that's being updated, so we won't get an accurate reading. So that's some possible improvements that we can make in the code. So that's the demo. Thank you for watching, and if you have any questions, you can email me at my email ahmedali.khan@mail.utoronto.ca. Thank you.